Hi everybody, I'm Greg Fishel. Welcome to bonus weather video number 2 for this week. And this whole week is going to be, or has been and will be and is, a series on radar and some of the interesting aspects of radar. And there are some limitations to it which you simply cannot get around. It's simply a matter of physics, and so you have to try to optimize what you can to work around those limitations. And there are some ways to do that. So we're going to talk about 2 of those today. And so let me go on ahead and put myself down here in the corner, and we will take a look at this little graph here. Now, this is the height and width of the radar beam, and the elevation angle is 0.2 of a degree above horizontal. So in other words, if the radar was sending out pulses directly parallel to the ground, right at the radar site, it would be 0. So 0.2 is 0.2 of a degree above that. Not much, but a little bit. And the more that, or the greater the elevation angle is, then the more rapidly the beam ascends in height as it goes out. And that can be a problem because you eventually reach the point at a certain range where you're going over top of most, if not all, of the weather. And so you want to keep that elevation angle as low as you can. The only problem is that the pulses that go out make up what we call a radar beam, and the red is the top of the beam, the blue is the bottom of it. And notice that the blue actually goes a little bit below 0, below ground level, and doesn't get back to 0 until 40 nautical miles. And so as a result of that, it is going to be bumping into things near the ground, such as buildings, trees, whatever, okay? And there are some post-processing techniques that have been developed, ground clutter reduction, if you will, where it'll take a look at an object, and if over a period of scans it doesn't move, then it assumes that, okay, that's probably not a weather element. That's probably a stationary object, and we're going to subtract that out. Now, if there's any weather that happens to be coincident with that building or that tree or whatever, and you cancel that out, you also are canceling out the weather, okay? And so, again, this can be an issue. At the Raleigh radar, they tend to keep the elevation angle a little bit lower so that they can remain as low as possible out at a certain distance. A lot of the other radars actually go at 0.5. Okay, so it's sort of a personal preference and what any one given National Weather Service office has found to be the most successful for them. Now, if you look at this here, once you get to about 60 nautical miles, the top of the radar beam is at about 7,000 feet, and the bottom is maybe at about 800 or 1,000 feet, okay? So the beam is getting wider as it goes out, and you reach a certain point where the resolution really starts to go to heck in a handbasket. Like if you're taking a picture of 4 houses looking across a lake and your camera has low resolution, it's going to see those 4 houses as one house, which you don't want to do. But a higher resolution camera, or a narrower beam width, if you will, is going to be able to tell the difference between house 1, house 2, house 3, and house 4. So again, we're getting higher and higher above the ground as we go out. That's not good. And the beam is widening, and that's not good because the resolution is not as good. And so this is the reason they space the radars the way they do. There are 2 other radars south and east of Raleigh. One is at Morehead City, and other one's at Wilmington. And so once you get beyond about 60 nautical miles from Clayton, where the National Weather Service radar is, then the Wilmington and the Morehead City radars start to pick up the slack, because anything beyond 60 from Clayton is probably going to be less than 60 away from Wilmington and Morehead City. So as long as all the radars are operational, then there's a nice overlap, which tends to reduce this problem of losing quality data out at a certain distance. Now, if you raise the elevation angle up to 0.5 degrees, that's what those dotted lines there represent. And look here, by the time you get out to 120 nautical miles, the top of the beam is at 22,500 feet. And if you have a lot of weather that's going on well underneath that, you're going to miss it. And the thing about tornadoes is you really don't want to get much more than, maybe a kilometer or 2 above the ground. Once you get above that, you may see rotation within the thunderstorm, or what we call a mesocyclone, but you're not going to be able to pick up the individual tornadic circulation. So as a result, again, farther away you are from the radar, the less chance you have of picking up things like that with any detail. Okay, one other thing I wanted to talk about was something called the Doppler dilemma, okay? And what this is saying is that the The pulse repetition frequency, or the PRF, and let me label these different things here. This is the range, okay, what we call the maximum unambiguous range. In other words, how far the radar can see before things start to get complicated. And then we have the PRF, which is the pulse repetition frequency, how frequently the radar is spitting out pulses. And over here, you have the maximum unambiguous velocity, okay? So what do I mean by maximum unambiguous range? Well, because it's different than just the normal range. What that means is if you have pulses coming out at a certain rate, okay, and then they bounce off an object and they come back to the radar, what happens if the next pulse goes out before the first one gets back to the radar, okay? The radar can't tell the difference. All it knows is that it's getting returns from two different pulses, and so as a result, something may be put in the wrong location. A given radar echo may be put in the wrong location. So it turns out that the lower the pulse repetition frequency, okay, then the greater the range you have before you have to worry about that, okay? So up here, the maximum unambiguous range for a pulse repetition frequency of maybe a little over 300 is almost 300 miles, okay? And then as the pulse repetition frequency increases, in other words, it's going boop, boop, and then boop, 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 and then boop, 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 like that, then the greater that PRF is, then the lower your range is. And by the time you get out here to a pulse repetition frequency of 1200, your range is only about 75 miles. But the greater the pulse repetition frequency, the greater the velocities you can measure, okay? So notice here, when the PRF is about 300, we can detect winds of, and you have to look at this axis here, of only about 15 miles per hour. But at 1200, you can detect winds of 70 miles per hour. But your maximum unambiguous range is only 75 miles at that point, okay? So again, it's another one of these trade-offs that you can't get around. It's just simply basic physics, where you want to have a pulse repetition frequency that is low enough so you can get a decent range, but you don't want it so low that you can't measure velocities, especially when you get into a situation with tornadoes and so forth, where you know the velocities are going to be very, very high. So this is called the Doppler dilemma, and there are several different scan strategies that the National Weather Service will have in order to try to figure out what is the optimal pulse repetition frequency. And there are even some radars, from what I understand, or some strategies you can employ where you actually have a dual PRF, where you're sending out one PRF to measure the distance of the objects that the radar beam is hitting, and another PRF to measure the velocities. And so there's all sorts of different strategies that you can employ to try to get around these physical limitations. So I hope you don't have to understand every detail about that, but I hope it just gives you a little bit of an idea as to what some of the limitations are with radar and some of the things these radar operators have to try to get around. Okay, that is bonus weather video number 2 for this week. On Friday, I'm going to be talking about how National Weather Service radars compare to television station radars. And is there as much of an advantage now as there used to be, okay? And what are the limitations of television station radars compared to National Weather Service radars? So I'm going to get into all of that. And again, this is not going to be a bashing session on TV radars. I used the television radar for many, many years at WRAL, but there are some things that I think are important differences to point out between those radars and the National Weather Service radars, and we will do that on Friday. Okay, folks, that is it for now. Let's see if I can advance this here. There are the credits, and that is the bonus weather video for today. Again, next one Friday, next daily weather update coming up later this afternoon. Take care, everybody. See you later.